Equilibrium temperature. The hot steel sphere is submerged into the bucket with the cold water. The task is to calculate the equilibrium temperature. This is a classic problem that you might have encountered in school physics book. The sphere initial temperature is 85 degrees Celsius and the water temperature is 20 degrees Celsius. We do not compute the fluid dynamics here. Our task only is to calculate the equilibrium temperature, and the heat exchange with the ambient is ignored as well. The body features not only the temperature, it also features the stored heat energy. So I need to specify the density for the bodies and the specific heat capacities. This type of task could be simulated with transient heat transfer model of QuickField. The only trick here is how to specify different temperatures, different initial temperatures for the bodies. Okay, let's start QuickField and see how it could be done. In QuickField, I create new problem. Bucket. Next. Problem type is transient heat transfer. Bucket features rotational symmetry, so the model class is axisymmetric. Length units are centimeters. Next. Here I should specify the integration time. Let's simulate 1 hour with a time step of 60 seconds. And the initial temperature is... Actually, I should specify different initial temperatures for the bucket and for the steel sphere. Let's put in here 20 degrees Celsius. Finish. Here in the geometry model editor window, let's draw a bucket. Click here, edit, add vertices. 0, 0. The bucket height is 20 centimeters. The bottom radius is 5 centimeters. The top part radius is 10 centimeters. Close, switch to insert mode and connect the vertices with the straight lines. Here, in axisymmetric problems, the axis of rotation is a horizontal one, and I should draw only the upper half of the cross-section. Now let's insert a sphere in the bucket here. This will be the center of the sphere. Click to select, insert shape, a circle with a diameter of 5 centimeters. Close, and I do not need the parts below the axis, so I remove this edge. Okay, now let's assign labels. Through labels you can explain the physical meanings of the geometric objects. Switch to select objects mode, click to select, this is sphere, and this is water. Okay, at the external boundaries, we have zero thermal flux boundary condition, and QuickField automatically sets this boundary condition at the external boundaries, so there is no need to assign labels to these boundaries. We have only labels assigned for blocks. Now let's provide physical properties for these blocks. Double-click the label in the tree. The sphere is made of steel with a thermal conductivity of 40, density of 7,800, and the specific heat of 460. And for the water, thermal conductivity is 0.6, density is 1,000, and the specific heat is 4,200. Now, what about the initial temperatures? In general, to get the desired initial temperature, we should simulate a separate problem. Let's assign labels here. Hold the Ctrl button, press to select several objects at the same time. Let's assign label +20. And here I assign label +85. And for this label, I specify the temperature +20. And for this label, I specify the temperature +85. Initially, the sphere and the water are not in contact. We can simulate this by adding a thin boundary layer between them. So I'm going to insert another circle with a diameter of 5.1 centimeters. I do not need the bottom part. Let's zoom in. This is the boundary layer. I assigned label layer. And for this layer, I do not specify any properties. You see the exclamation mark next to the label name. The temperature distribution will not be calculated in this layer. So now the water and the sphere are insulated from each other. And I need to remove the label from this edge belonging to the layer. None. None. Okay. Let's simulate this problem. Build the finite element mesh and solve the problem. Let's take a look at the results. Okay. We have got the desired temperature distribution, +20 in the water and +85 in the steel sphere. Let's zoom in, and they are not in contact. Now let's create another transient problem, and this new problem will take the temperature distribution as an initial temperature distribution. I create new problem, bucket cooling. Next. To be able to automatically pass the temperature distribution from one problem to another, both problems should be based on the same geometry model file. The geometry file was called bucket mod. So here in the problem properties, I should browse, and here's the file. Problem type is transient heat transfer. Model class is axisymmetric. Length units are centimeters. Next. I'm going to simulate 1 hour with a time step of 60 seconds and the initial temperature, again, 20 degrees. Actually, I'm going to import the temperature distribution. This one. Finish. Okay, the geometry model is the same and the labels are already assigned, but the data file is different. Actually, I can copy the labels properties here for the water and for the sphere. And for the layer, I'm going to specify now the properties of the water. So now the sphere and the water will be in a contact. 1000, 4200. Okay. And I do not need temperature here anymore, so I do not specify any values here. This is 0 mark next to the label name. Okay. Now I need to add the link. I need to link two problems. Follow to the problem properties, links, generated heat. No, I need the temperature field. And the temperature field I'm going to import from bucket. Add. And the moment of time I would like to import to is 3600 seconds. Update. Okay. Now you see I import the temperature field from the bucket problem, and the time when the temperature was calculated is 3,600 seconds. Let's take a look. Yes. I'm going to import exactly this temperature distribution. Now let's solve this new problem. Let's take a look at the results. Here you can see the temperature distribution after 1 hour of cooling. Let's take a look at the initial temperature distribution. Initially it was 85 degrees here and 20 degrees in the water. Remember, I do not simulate fluids dynamics here. So in fact, if you take into account the natural convection and the gravity, the temperature distribution will not be this one. But here I'm only interested in the final temperature distribution, in the equilibrium temperature. As you see, the temperature distribution is not yet uniform, so I need to increase the integration time. Let's simulate 100 hours with the time step of 1 hour. Yes, run the analysis. Okay, let's take a look at the results. Now we have got the equilibrium temperature. The temperature is, let me check, 21 degrees Celsius everywhere. Initially, the temperature distribution was plus 85 in the sphere, plus 20 in the water, but then gradually the temperature redistributed and the sphere cooled down. You can see the dynamics on the time plot. Right-click any point and choose the time plot. You will see how the temperature in the sphere changed in time. If you search for the equilibrium temperature on our website, you will find the example page. Here you can read about problem setup, browse the solution section, take a look at the result pictures, and download the simulation files. Simulation files may be opened and the results may be viewed using any QuickField edition, including QuickField Student Edition, that you can download from our website for free.